ask ourselves here, what happens to the area and perimeter when we change the dimensions of a figure? So today we're going to change the dimensions proportionally, and tomorrow anything goes. We're just going to change a dimension and we're going to find out what happens, what is the effect on the area and the perimeter. Okay? An example would be, right now I am remodeling my bathroom. And so I had the option of, let's say, making my shower a little bit wider while they were already in there demoing everything. Well, if I made my shower wider, let's say I pulled it out by 2 feet, how much more tile would they have to go by? And which tile am I going to use? Because if I change the length by 2 feet, how does that change the area? That kind of thing. So this is applicable to the real world. When you change one thing, what does that do to the perimeter? What does that do to the area? Each of you should be given an index card. Stop making fun. Oh my gosh. Each of you have been given an index card. I want you to measure the dimensions of the index card and calculate the area and perimeter and write it down. Yes, you might already know the basic dimensions of a note card. So if you have a ruler, use a ruler. If you don't have a ruler, then we will talk about together what the dimensions of a note card is. Inches, please. Inches, inches, all day today, inches. Very nice. Okay, so the dimensions are 3 by 5. The perimeter, 16 inches, and the area, 15 inches squared. Okay, next step, you either have 4 people at your school or you don't, that's okay. Now I want you to put 4 index cards together, and I need you to make a rectangle that has double the dimensions of your index card. So you're making a new rectangle, but it can't just be any rectangle. It has to be a rectangle that has double the dimensions. So you're making this rectangle. The dimensions are doubled, and now I want you to find the area and the perimeter. Okay, so here's what we should have found. Oh, we're not going to do that one yet. We're going to do this first. Okay, so the original dimensions were 3 by 5. The new dimensions were 6 by 10. So what was our scale factor? Our scale factor was 2. We were doubling. Our original perimeter was 16. Our new perimeter should have been 32, although I don't think that's what you typed. Anyways, if I write that as a ratio, 32 to 16, what does that reduce to? 2 to 1. You can put it in your calculator. Just like if I put my sides here, 10 to 5, it also reduces to 2 to 1. Now let's do the areas. The original area was 15. The new area was 60 inches squared. So if I did the ratio of the areas and asked my calculator, math, enter, enter, you reduce to 4 to 1. So what's pretty cool is that the ratio of the sides equals the ratio of the perimeters. Are the sides the same? No. Are the sides the same as the perimeter? No, it's 10 and 5 and 32 and 16. The sides and perimeters are different, but they reduced down to the same thing. 2 to 1, 2 to 1. When it changed is when we went to area. When we went to area, it became 4 to 1. Why is that? Why do these match and this one's different? Because area is weird. So we're going to do that other one in a moment. Don't put your note cards away. So we just discovered the ratio of the sides. If the ratio of the sides is A to B, then the ratio of the perimeters is A to B, and the ratio of the areas is A squared to B squared. Go ahead and put that in your notes. And while you're writing that down, we'll talk about it. Sides of a figure. Length, width, height, diagonal. All of those are one-dimensional things. Length, width, height, side, diagonal, they're all one-dimensional things. When you add them all up, you don't change dimensions. When you plus things, when you sum, when you find the sum, you don't change the dimensions. So the sides are all one-dimensional. Perimeter is a one-dimensional value. But when you find the area, when you fill in the shaded region, that's two-dimensional. So you can think of these as, some people write it as a scale factor of k. This would be k to the 1, and then k squared if k was your scale factor. Because it's one-dimensional, two-dimensional. And yes, Alex, when we get into next unit, the ratio of their blank will be k cubed. What? You already said it. Ratio of their volumes. But we'll get there when we do 3D or 3D unit. We're still in 2D. Okay, let's see if it works when we get smaller. Take some scissors, or you can just fold. If you want to just fold and shade, that's good with me. I want you to take your note card, and I want you to half the dimensions, both of them. I want you to form a new rectangle that is half the length and half the width. So, like, find the middle of your length and put a little dot. Find the midpoint of your width and put a little dot. And then connect those. I'm just using my pen. I'm not using scissors because I don't know if y'all have scissors. Yeah. So what's crazy is all I did was half the dimensions. I'm like, okay, I want them to be half as big. Half the dimensions. But my area was not halved. What I got out of having my dimensions was something much smaller. So when you play with your dimensions, you affect your area way more, right? Not really. Your mind shouldn't be blown that much, but it is important to note. If you say, oh, make those half the side, you're playing with the area more than you think. So I halved the dimensions, half the length and half the width. But since it's 2D, since it's two-dimensional, it's not affected by 2. The area is affected by 4. So when this should say halved. Is that with a V or an F? I don't know. So when I have my dimensions, what's the scale factor of the new dimensions? It's 1/2. What's the ratio of the new perimeter to the old? 8 to 16 reduces to 1/2. And what's the ratio of the areas? Well, your calculator can tell you that 3.75 to 15 is not 1 to 2. It's obviously 1 to 4. So this is like 2 to the 1, 2 to the 1, and 1 to 4 is like 2 squared. 2 squared is 4. Let's try some examples so that this can make a little bit more sense. Find the ratio of the sides. Okay. When it does ask you for a ratio, I don't care which one's first and second if the problem doesn't specify. So it says ratio of the sides. You can do 28 to 16 or you can do 16 to 28. Doesn't matter. What does matter is that you reduce. Do not leave a ratio unreduced ever. So the reduction of that is, thank you, Toby, 7 to 4. So the ratio of the sides is 7 to 4. Here's where the beauty of the lesson comes in. I don't need to find the perimeter of this square and the perimeter of this square and divide them and reduce them. So that's 1 step, 2 step, divide them, reduce them. It's like 4 steps. We get to skip all 4 steps because we learned that since sides are 1D and perimeters are 1D, they will reduce down to the same ratio, even though the sides and perimeters are not the same. So, what's the ratio of the perimeters? Thank you. I did not find a single perimeter, and I automatically know the ratio of their perimeters. Okay, how do I find the ratio of their areas now? 1D, 1D, 2D. Do I have to find the area of that square with side 28? No. I can just take my ratio, A to B, and square it. A squared to B squared. So what is the ratio of the areas? Yep. And that does not reduce, so that's our final ratio. So we get to skip steps here. This lesson is about skipping steps. Pretty nice. Let's look at this one. Now notice, every time we do these, this is all hinging upon the fact that our figures are, they don't have to be regular. They can be really irregular. Like it can be this triangle here and this triangle here. And I don't care if they're regular, but I care that they're similar. If the figures aren't similar, then these little tricks and shortcuts do not work. Okay. Notice what we're given here. We are given areas. We're given the 2D. So the ratio of the areas, I always do second over first. But like I said, you can do that in any order. Does that reduce? 169 divided by 100, math, enter, enter. Doesn't reduce, so we leave it that way. This is 2D. How do I go from 2D to 1D? How do I go from a squared to b squared to just a to b? Square root is the opposite of squaring something. Yes. Square root of 169. Square root of 100. And then what's the ratio of the sides? Do you notice that we never once touched our formula chart? Do you notice that honestly, we didn't even care that these were hexagons? Because they were similar, we were using the proportional change. We're using the fact that they're proportional. We didn't need to use apothem times perimeter divided by 2. We didn't need to find the perimeter knowing that it had 6 sides. We got to skip it. Pretty cool. Next example. So we want to find the perimeter of the smaller rectangle. Remember, on these problems, since they're similar, there's a long way and there's a short way. I could find this missing side. Yep, I could use the perimeter in the side and I could work backwards. I could find the missing side. I could find the scale factor. I could use the scale factor to convert it to this missing side, and then I could add up all the sides and find the perimeter. So I could do 4 steps. Had I never learned this lesson, I could solve this problem. But with this lesson, we're able to get there a little bit quicker. We're able to say, I know that the ratio of 15 to 12 is equivalent to the ratio of 115 to x. Because even though one of those is sides and one of those is perimeter, sides are one-dimensional and perimeter is one-dimensional, so they are going to reduce to the same ratio. Cross multiply is really your only step. 12 times 115 divided by 15, and you're done. The perimeter of the small one, without ever using a perimeter formula, is 92 inches. Yay, we love shortcuts. Ooh, octagons. Given 2 similar octagons, find the area of the larger octagon. Hint, do not draw an apothem. Let's begin this problem like we began last problem, okay? So let's say I know that the ratio of my sides is 9 to 15. Those are sides, so those are one-dimensional. And I'm going to compare circle is to circle as underline is to underline. I'm going to compare the ratio of my areas. Now I have to be really careful because sides are 1D and areas are 2D. I put little bubbles above each ratio so that I can keep track of what dimension I'm in. So in one side of my proportion I'm 1D, and in one side of my proportion I'm 2D. You cannot cross multiply. Promise me, you will never cross multiply a 1D with a 2D. You can't. It's not allowed. Yeah, you're in multi-universes. Yes. Okay. So what you ask yourself is, what do I want my final answer to be in? Well, look at x. X is in the 2D column. So I need to convert everybody to 2D, then everybody will be happy, and then we can cross multiply. So how would I get this column in 2 dimensions? 2D. I get there simply by squaring it. If you want to get to 2D, you square it. If you want to get away from 2D, you square root it. No, you don't have to square those and reduce it and then cross multiply. You can go straight to your calculator. 15 squared times 45 divided by 9 squared. But if you cross multiply before making your dimensions match, you're guaranteed to get the wrong answer. Your dimensions must match. Twinsies, matching. D match. Okay, final answer. Final answer is 125 centimeters squared. Another way we could have done that is we could write the units at all times. You could write your units, and then you would have a big clue. Oh my goodness, one of that side is in centimeters and that side is in centimeters squared, and those don't go together. So if you have a habit of writing your units, you can see automatically that you're not allowed to cross multiply yet until you square. I told you there was more pizza problems. The pizza problems are out of control. I need to turn some of them into like blueberry pie or something. Lauren ordered 2 pizzas. The diameter of the smaller pizza is 1/4 the diameter of the larger pizza. What can you conclude about the surface areas of the pizza? Very good. So we need to look for some keywords here. This is a key word, this is a key number, and this is a key word. Now, we don't need to pay attention to the word surface. You can't really say, oh, the area of the pizza is this, because pizza is a 3D object, so I did have to say surface area, but we don't need to worry about that yet. Diameter is a length. It's a segment. It is one-dimensional. So my 1D scale factor is 1/4, but it's asking what happened to the area. And we know when we make the diameter smaller, just like this note card, it doesn't make the area 1/4 the size. It does crazy things to the area. It doesn't just fourth it, doesn't cut it into fourths, it cuts it into 16ths. So the area of that pizza, which probably would never happen in real life, would be 16 times smaller than the area of the big pizza if you mess with the diameter that much. Last problem. It's spring. It's gardening time. A gardener is planting tulips in rows in her 2-foot by 5-foot rectangular garden. If she plants 30 tulips in the garden, how many tulips would she plant in a 4-foot by 10-foot garden? Yes, you could draw the garden out. You could draw the tulips lined up. You could draw the new garden, and you can calculate it that way. But once again, that would take much longer. Let's start with finding out what happened to the dimensions. What happened to the dimensions? 2 by 5 became 4 by 10. Good. They were double. The dimensions were times 2. That's 1D. Now, she's planting the tulips in rows. So is that a 2D thing or a 1D thing? Is it going along the edge? Is it perimeter? No, it's area. No, not 3D. She's not planting them high. She doesn't have different levels. So the 30 tulips, normally we would just do 30 times 2. But 30 is area and 2 is dimensions. So I am not doubling the amount of tulips. I am what? We need to make them match. This is 2D. This is 1D. We need to convert everybody to the same thing. So if I convert that to 2D, I have to square it. So how many would she get to plant? 120. Yes, correct answer. 30 times 4. 30 times 2 squared. One other thing you could have done, if you didn't like the way I did that, is you could find the area of this garden. The area is 10 feet squared. Ooh. And you could have found the area of this garden, which wouldn't have taken very long. Now this is 2D. What's the scale factor? 2D. 40 divided by 10. So the scale factor is 4, and that's already in 2D. So that's another way you could have done this problem. Not bad. Proportion will work too. Yes.